Okay, so I hope the recording is on now. All right, so what we will do today is the hierarchical clustering, which is the high dimensional clustering, part of the high dimensional clustering. Then I hope my voice is clear. I hope you can hear me.
Yeah, you're very much audible.
It's clear, right? Hello.
Yeah, you're audible.
Okay, all right. So as I was saying, today we will do this. We will be talking about this hierarchical clustering. And then after that, um, we will deal with this dimensional reduction. I will give you an overview of how you should go about it because the final project you'll be doing will be around that. So I actually prepared to teach that, but I will give you an overview of that. Then I want you to actually learn most of the concepts by yourself instead of me just giving it to you. I just want you to learn most of the concepts here by yourself. This is one of the important things that um, is good to know for principal component analysis. So I'll give you an overview of that. And then after that, I will load a project which regards you to actually reduce the dimensions before you can proceed to do that. So we'll see how that one is going to be done. So let's begin by talking about this hierarchical clustering. So last week we dealt with the K-means clustering. Then after this hierarchical, we will be having this dimensional reduction. All right. So let me go to this. So this is what we did last week. This is what we did last week. Let me quickly recap it. So we were dealing with clustering, that is grouping the items into different groups or different clusters so that we can actually separate them based on their similarities or based on their distances that are closer to each other. And then since we're dealing with Kmeans, we're talking about centroids, where we actually put centroids in the middle of these data points and then try to associate each data point to one of the clusters based on the distances that are closer to each other. So as we talked about last week, we have connectivity-based clustering, which hierarchical clustering is under that. Then we have centroid-based clustering, where we have K-means clustering, which we dealt with last week. So this is hierarchical, which we are going to talk about in a minute. So for K-means, we just put centroids. Then we associated the points to these centroids. And then we also figured out how we are going to use the airball method to actually find out the number of centroids that we are supposed to put. If you remember the Jupyter notebook that we did, we actually, this is the technical support data set that we dealt, where some of the complaints, we were able to group them using, we used the airball method to actually figure out the number of clusters that we are supposed to get. And then after that, okay, someone is in waiting room. Let me admit the person then. Okay, so we figured out how many centuries that we need. Then after that, we're able to group these complaints into different clusters. That is, those that are in cluster 2, those that are in cluster 0, and so on and so forth. So that's K-means for you. We use the concept of centroid. Now for hierarchical clustering, we actually, as the name suggests, we build hierarchy, which associates each of the hierarchies with each data point.
Mr. Great, sorry to interrupt you. In the last sessions, what we talk about K-means clustering, I have one question.
Okay.
That the distance measuring technique, like Euclidean distance or Chebyshev or cosine, in that, which distancing measure is relevant to my data set? How do I understand that?
Okay, so for the distance measures, you can actually, so for using the distance measures, it's kind of a hyperparameter that you can also tune to get to know. But mostly Euclidean works for, I mean, most of the data sets, unless maybe you're doing, as I said, you're doing recommendation systems. That's these kind of distances doesn't actually work effectively, except cosine similarity that actually work when we're doing recommendation systems. But apart from that, um, the calculations of these distances are almost the same thing. They approximate to the same results. And mostly Euclidean works for almost all the data sets. So to be on the safer side, I will suggest mostly go with Euclidean distance. Like 90% of the time you just use, if you're not sure, you can even leave it to the default, and the default mostly is even Euclidean distance. It's either Euclidean or Chebyshev, because Chebyshev is a generalization of all of them. So you can also leave it to the default, where you can also use the Chebyshev to do that. So mostly it's not about that the data set and which distance I'm supposed to use, but they all approximate to the same results for you. So if you're not sure, you can leave it to the default, because the default will be either Chebyshev or Euclidean, and Chebyshev is a generalization of all of the distances.
Okay.
Mm. So we will move on to now talk about the hierarchical. So as I said, the name itself suggests what we are actually talking about. That is it forms a form of a hierarchy. So let me just give the example that we did last week, so that we can move on from there. Okay. I hope my pen is visible. Okay, so if you can see my pen, I'm writing. If you cannot see, let me know so that I'll adjust it. So from last week, we actually talked about where an instance where we have a data point, maybe one data point here, and then maybe another one here. So we can even call this one, say, point A. Then we can call this, say, point B. Then we put also another point somewhere here. Then we can call it point C. Then maybe another point, one here, another one here. We call this one E, this one F. And then maybe we can put the other one here. So this is the example that we used last week. And then we say that for connectivity base, we are dealing with connectivity, right? Connectivity, an example of connectivity based clustering, that's the most popular one, is the hierarchical clustering that which we are dealing with right now, right? So connectivity is just connecting them, the ones that are closer to each other, we connect them like that. So from here, we can even say that maybe these ones are closer to each other, we can connect them, and then maybe we can move forward and then to connect them. Then maybe finally we can connect everything together into one cluster. That is if we want a whole cluster. So this kind of connectivity where we connect each of these points. Okay, so as I said last week, we can also connect it using what is called the dendrogram. So if we have the point A, let me move down a bit. So if we have a point A, and then we have another point B, and then we have this point C, then we have another point E, then we say we have another point here, F, right? So now if we say that A and B are closer to each other, we can connect them. We can also connect, say, E and then F, and then we can see that C and then E and F are closer to each other. Then finally, we can connect everything together. Right, finally, we can connect everything together. So just like we did with the circle here, where we can finally connect everything here together, the same thing we can do also here. All right, so this is what we call the dendrogram, and this is in the form of a hierarchy, right? It's in the form of a hierarchy. So we call it hierarchical clustering. We cluster them according to how similar they are, right? We cluster them according to how similar they are. That's why we refer to as hierarchical clustering. And there are two main types of this hierarchical clustering that's we are going to talk about right now. Types of hierarchical clustering. So we have what is called the agglomerative. The agglomerative clustering. Then we have what is called the divisive. So we have these two main clusters. So as I said, let me pick them one by one so that it will be clear for you. So I'm going to do with this one first. So with this one, it starts with the individual points, right? The main catch here is that it starts with the algorithm will start with the individual points, right? And then after that, it will connect each of them to form a big cluster, right? It will start with individual points, then it connects each of these points to form a big cluster. So for instance, if we have a point here, then we have, let's say we have another point, just like we're dealing with later on, right? So what we can do over here is to actually connect, we can actually say that, okay, this one is one cluster, this was one cluster, this is another cluster, this is another cluster. Now we can now connect these ones, the ones that are maybe closer to each other, we can say these ones are more closer to each other. Then later we can connect this, right? Then finally we can connect all of them together. So that's what the agglomerative clustering will actually be doing, from individual to the big cluster, right? So it will move from each of these individual points to the bigger cluster. That's basically what it will actually do. And then for the divisive, as the name is actually suggesting, it's just like a division, right? So for that, it will start with a big cluster. Then it will divide it so it gets to the individual clusters. So it will be having a whole big cluster like that. It will be having a whole big cluster like that. Then let's say we have a point here, just like we just did. So I'm just going to do the same thing over here. Then it will say, okay, these points are, let me use this, these points are closer to each other. It will connect this one. And then maybe these ones are also closer to each other. Then after that, it will say that to now consider these points individually, right? Maybe I should have used different. It will now connect these ones individually. Okay, so now moving from this big to that, then to the individuals, right? Moving from the big cluster to grouping them together, now going furthermore to individual points like that. So that's the divisive. So from big to individual clusters. And then for agglomerative is from individual to the big clusters. So that's basically the two forms. So moving from the point, right, like we did last week over here. Okay, let me just do it quickly. We had this, let me do this. So we have points, right? We have several points like that. We're having these several points. Now, if we want to associate these points, right? Let's say we have centroids here. We have one centroid, we have another centroid here. Now, if we want to associate these points, right, to these centroids, right, it's not that a big deal, as we just use the distances from each point to measure the distance between each point to the centroid, right? It's not difficult. It's not difficult to do because we already have in a way to do that. It's actually easier for the various distance measures to do, right? Now the problem is if we have cluster like this, now let's say we have this cluster, let's call this one 1 and then call this one 2. Now, if we want to associate this cluster with this cluster, we want to measure the distance between this. That's where the problem comes. Measuring each point to the centroid is not a big deal. But if you want to measure from one centroid, from one cluster, a whole cluster, to another whole cluster, that's where the problem is. And there are several ways that we can go around this. So I'm going to show you some of them over here. So we have. I hope you can see the image on my screen.
Yes.
Okay, so we have several ways that we can go about it. One of the ways that we can go about this is let me change this, is the single linkage, right? So we can find a link between each of the points that are in each of the clusters. So for instance, if you see these ones, right, each of the points, so we can find a link between each of the points and the other, right? We can find a link between them and then measure the distance, right? That will give us the single link, right, or single linkage if you want to call it that way. So the distances between each point that are closer to each other. So this is one cluster. Let's say cluster A, and then a cluster B here, right? So this point is most closer to this point. So we find the distance between that point, and then we use it as a measure of the whole cluster being closer to this cluster. So the distance between this point and that point becomes the distance between this cluster to this cluster. Okay, let me just take it one more time. What I'm saying is that if we want to find the distance between the whole cluster, the whole of this cluster A and the whole of this cluster B, right? What we do is that one of the ways that we can do it is that we find the distance between the closest points of each of the clusters. So we find a point which is here, which is closer to a point which is here, and then measure the distance between these 2 points. So let's say this one was maybe 2 centimeters, right? Let's take it for example. So this 2 centimeters, we assume that is the distance between the whole cluster, right? Between the whole cluster. So we take the distance between each point and then generalize it, right? And then the other way that we can do is the complete link or the complete linkage, which is we find the distance between the farthest points, right? The point that is very far from each other, right? The last point that is far from each other. Then measure the distance. So maybe this one will be maybe like 10 centimeters, right? then we say that, okay, this 10 centimeters is the distance between the whole cluster, right? Between cluster A and then cluster B. So this is another way that we can also do it. And then we can also consider the average of each of the distance between each of the points. So if we take this point, we measure the distance between this point and this point, between the same point and that point, between the same point and this point. So between the point and each of them, right? Then we move on to the next point. So maybe this point, that, the same point, that, the same point, that, the same point, that, the same point, that. Then we pick another point again, the same point, that. We measure the distance between each of the points and each of the items in the other cluster. Then after that, after finding it for each of them, we find the average of it, right? We find the average of it. And then we say that that average, maybe we find the average and then we get about, say, 6.2, right? That 6.2 units or centimeters becomes the distance between each of the clusters over here. All right, so that's another way that we can also do. And then there's this centroid one, which is quite popular, right? So just like we were doing in the Kmeans, right? In the Kmeans classroom, where we find the centroid and then measure, we find the centroid and then measure the distances between each point to the centroid, right? The same way we will find a centroid for one cluster. That's, if we take this as cluster A and then cluster B, we find a centroid for this, we find a centroid for that, and then we measure the distance between each of the centroids. So if we find, say, 8 units or 8 centimeters here, this distance becomes the distance between this cluster and then that cluster. I hope it's clear.
It means that, as would it is similar to Kmeans itself.
I did not get you. Can you make your voice a bit louder?
Yeah. Am I audible now?
Yeah, yeah.
Yeah, it means that it is similar to Kmeans itself. So,
okay, we use for centroid here, yeah, we use K-means to find the centroid here. We use the concept of K-means. That's the how we find the centroid for K-means. We use the same concept here to find the K-means. I mean the centroid over here, and then after that we find the distance between each of the centroid. So that's
okay.
one of the ways that we can also use to find the distance between clusters.
Got it. Got it.
Okay. So now let me just go a little bit back here from, I think, this one. Yeah. Now, if we take this, okay, I messed this one up. So let me draw it again. So we're having point A, then point B, then point C, then we're having D, and then point E. So we say that A and B are closer to each other, D and E are closer to each other, C is more closer to D and E, and then this one is also closer to that. Okay. Now, over here, if you do this this dendrogram, right? If you are doing your algorithm and then you do this dendrogram, there's one more problem that you might be encountering over here. Now, if you say that this is just a simple example, you might be seeing some dendrogram that will go, and then you might be seeing it small, something like that. Some of them you cannot even see them. They might be a little bit messy, something like that. A lot of them like that. Now there's a problem with that. There's a problem with this now. If I say that if I put a line here, mostly it will be in a two-dimensional space. So let me say let me do this. Now if I put a line here, right? If I put a line here and I cut my cluster here or my dendrogram here, it means that I have these two clusters. I'll be having this cluster one here, which is this one, which will be containing this part. I'll be having another cluster here, right? So I'll be having two clusters if I cut it here. Now, if I don't cut it there, and then I come and cut it here, let's say I cut it here, right? If I cut it here, I'll be having this cluster. I'll still be having this cluster here. So maybe I can still call this one 1. Then I will still be having this, I will also be having this cluster. I can call this 2. I'll be having this cluster 2. I'll be calling it 3, right? Now, if I come down, then maybe I cut it here, right? If I cut my dendrogram here, right, I will be having this cluster, maybe cluster 1, cluster 2, maybe this one will also be having its own, right? This one will also be having its own. I'll be having cluster 3, cluster 4. Now, depending on where you are cutting it, you'll be having different clusters, right? And that's one problem. And there's a way to go about it. There's a way to actually tune the hyperparameter to get the right clusters that you want. There's another problem too. Now, if we are doing this clustering, right, as we talked about over here, we have different ways that you can measure this distance. Now, if I build the algorithm and then I use the first one, I use single linkage, right? If I use single linkage, I'll end up with a different dendrogram, right? From someone who will also be using complete linkage, from someone who will also be using this, from someone who will be using this. And this is also another caveat which is associated with this kind of dendrogram and this hierarchical clustering, which you need to take into consideration. Now, there's a way to actually go about this, and one of the ways is what's referred to as cophonetic correlation, right? Now, this is just a word, not anything big. What it's saying is that if I have my data points, let's say we have our data frame like this, right? Then I have a point. So this one might be x1, x2, x3, x4. Maybe our targets will be say y here, right? So something like that. Different rows. We might be having different rows over here. All right. Then we might be having different points. Now, let's say we have let me represent this one. We're having A and then B, right? Now, let's say the distance between A and B. So I'm just going to use the distance instead of giving all the points over here, right? I'm going to use a distance measure here. So the distance between A and B will be, we will use the Euclidean distance, right? We use the Euclidean distance measure to do that. So let's say we did Euclidean distance. So just forget about these ones over here. I'm just going to give only 2 points over here, right? So let's say we measure the distance between from A to B, right? And then we got say 3.2, maybe 3.2 centimeters or 3.2 units or whatever unit is being measured. Now, let's say the distance between, let's pick D and E, the distance between D and E, right? Let's say that's one. We got that one to be say 6.3. I'm just choosing random numbers, just random numbers. Now I'm choosing. Now, these are the actual distances. Let's assume these are the actual distances between A and B, and this is the actual distance between D and E, right? So if we move from A to B, let's say that's the actual distance. The actual distance is 3.2. Let's assume that. And then let's say if we move from D to E, the actual distance is say 6.3. Let's assume that I just choose A and B and D and E randomly. I could have also choose maybe B and C or A and C or A and D. I could have choose any of them. Okay. So now let's say this is the actual distance. Let me make it a bit neat over here. A, B, D, E, right? So the distance from A to B, the distance from D to E. So what I said is that we should assume that this is 3.2. Let's assume that this is 6.3. So this is the Euclidean distance. Okay. Now we also have the dendrogram distance. All right. If we do this in a 2D here, we will be having some numbers here, maybe from 0, maybe 2, 3, 4, 5, something like that. All right. So I'm going to draw a clean one here so that it will be a bit. Okay, so we're having our A and then B, we're having C, then we're having D and then E, right? So we connected this and then we connected this one, right? Then we connected this and that, then we connected this and that, right? So over here, normally this A and B should be on the x-axis. Okay, so let's say we have this and then we have some points here, maybe 1, we have some 2, we have some 3, we have some 4, something like that. So the dendrogram distance, so if you want to find the distance between A and B on the dendrogram, then it is this line here, right? A and B meets here, right? Both of them meet here. Let me change this so that you can get it. They all meet here, A and B meets here, right? So we can measure the distance here. That is the line here, right? To see the distance. So where this line is the dendrogram distance, right? So for instance, this one might be maybe 2.5, right? So the dendrogram distance over here will be say 2.5, all right? Now, if we want to see say the D and then E, right? The D and E maybe somewhere here, hypothetically, and the normal circumstance, it will be a little bit bigger or a little bit lower, right? Maybe not as close as I am measuring here. Maybe this one will be say 2.8, something like that. 2.8. Now, what this cophonetic correlation is saying over here is that if we find the correlation that is between this value and then this value, right? The correlation that's existing between these values, and then if it is higher, remember correlation. If we have say 0.8, right? It's a high correlation, right? It's high. If we have say 0.002 is very low, right? So the more you get closer to 1, right? The more you get closer to 1, the more it's high, right? The more you get closer to 0, then it's less, right? So if we find a correlation that's existing between the Euclidean distance, that's the real distance that we will measure on our data frame, right? That we will measure on our data frame. And that distance is more correlated to the dendrogram distance, then we can say that the particular dendrogram is correct. So under normal circumstance, what you do is that you don't build one dendrogram. Maybe you might build another one, right? You might be building another one, which is also having its own, like that, right? Which is also having its own something like that. Now you compare this, you find the cophonetic for this, correlation for this, then you find the cophonetic correlation for this one too. And then you see if this one is maybe 0.7 and this one is say 0.6, then you can choose this one over that, right? You can say that this one is better than this one because the distance between the actual data points is a real representation of what you're seeing on the dendrogram. All right. So under normal circumstance, you might be having these data points. As earlier on, I wanted to do that, but I wanted to show you this one first. So if we have our x1, our x2 here, our x3 here. All right. So these x1, x2 are just something. It could be maybe a customer's age, a customer's sex, right, or a customer's monthly income, something like that, right? It could be anything. So let's say we have some data points, 300, maybe 72, maybe 40, something like that, going down like that. Maybe we have another point here, maybe 10, 15, say 30, something like that. Maybe we have 20, 25, say 17, and then maybe we have say 1, 0, maybe or maybe 0.01, maybe 11 here, maybe 14 dash dash dash. Then maybe this one is 0, 1, 0, 1, 0, 0. That's our target, right? So now the distance is, so the AB that I'm talking about is these points, right? So maybe this point represent A, this point represent B. So these letters that I'm using are representing these data point that you can see on your data frame, right? So the distance between this, right? So if you measure the distance between this A and B, that's 172. Remember, if you want to measure this distance, is if you use the Euclidean is going to be say 100 minus 72 square, right? Then plus the next data point, which is 10, all right, which will be 10 minus 15, right? 10 minus 15 square. That is 100 minus 72, right? Then 10 minus 15, then 20 minus 25. So plus 20 minus 25 square plus 11 minus 0 0.0, 11 minus 0 0.01 squared plus, then the last, no, this one's our target. So we can ignore that, right? So we can ignore that one. And then we find the root of that. Okay, so that's what Euclidean distance will actually do for us. So that's the final distance. The final distance, maybe we calculate this and then we got this data point that we put there, 3.2. Right, so this 3.2 will be the result of this. Right, so that will be the distance between A and B. So this A and B, let's say we have another point here, which is something like that. So that will be the distance between this two row. All right, and then after that, if we plot this dendrogram, then we compare the distance that we are getting from this dendrogram with the real distance that we have in our data frame, right? Then we find the correlation that is existing among them and then see if they are closer or not. How we are going to see they are closer or not is depending on the value that we will get. So the higher it is, the better it is, all right? So if it is 0 0.7, 0 0.8, 0 0.9, then we can see that it's good. Normally, you are not going to get a perfect one to be, say 1, right? To be perfect. It's quite not real for you to get something like that. All right. And if it is getting closer to 0, say 0 0.4 or 0 0.0 or 0.3 or 0.01, then it's actually not a good representation. All right, so that's one way that we can actually use to represent. So let's go to the Jupyter notebook and then see what we can do with this one. I hope this part is clear before we go to the Jupyter notebook. Oh, someone was okay. I think Sanjay was on waiting room. Okay, I just admitted him, but he waited for long. Okay. This is what we have over here. We are going to implement the same thing, the same concept that we just talked about over here. Right? The same concept that we just talked about over here. This is what we are going to actually implement over here. And don't forget what we also talked about here with the centroid and then the complete linkage and single linkage. So if you see anything like that in the Jupyter notebook or in the code, then you can easily understand that. All right, so these are the normal things that we normally do when we are doing our Jupyter notebook right from day one to today. So the first thing we do is to import the various libraries that we're going to use. So over here, we started with pandas, numpy, matplotlib, and scipy. I mean, from Z-score, we need Z-score for normalization, and then we are also going to use Seaborn here um, for plotting graphs, right? So these are the normal libraries that we use, unless someone not understand and want us to go through that. So over here, we started by loading our data sets, right? We started by loading our data sets, and then we store it in a variable called df. Then we visualize the first 10 rows, right? So this is what we have. We have some customers over here. We have the customer's ID. And the normal circumstance, I would have dropped this ID immediately. And then we have the name of the customer. So over here, the names of the customers, we represent them with A and then B, right? So you can see customer A, customer B, customer C, customer D, all the way to the last one that we'll be having. Don't forget, we are just visualizing the first 10, right? Then we have the average monthly spend of each of the customers, and these are in dollars, right? So the first one is 10,000, right? $10,000. Then we have these spendings for other customers as well. Then over here, the number of visits that they visit in the store is also being recorded, and then the items that they buy. So some buy apparel items, right? Some buy food. FNV here is just fruits and vegetables, right? So fruit and vegetable items, yeah, mostly groceries, all right. Then staple items also over here. Okay, so this is our data set that we are going to deal with from here. So over here, what I'm doing over here is to actually pick everything, right? Pick all the rows. So if you can see over here, we are picking all the rows. Let me pick red. We are picking all the rows. So that's why you can see this over here. And then we are starting from the second column, which is this one actually. So we have 0, 1, 2, and then 3, 4, 5, and then 6, right? So we are starting from here and then picking everything. Okay, we are starting from here and then picking everything. So what we are not picking is these ones. So as you can see over here, you can see from, let me go a little bit down so that you can see. Now after that, if we print the head of it, right? If we print the head of it, we can see that it's starting from average all the way to the last one, right? Unlike at first where we're having the customer ID and the name over there. So that's what we are doing over here. Then from there, we want to normalize it. Now, if you look at something over here, right? If you look at something over here, the monthly spend, it's 10,000, 7,000, 7,000, 6,500, all the way to the last one that we can think of, right? But if you see the other data points, we have 2, 3, 7, just small values over here. Now, if you want to find this distance, as I think last week someone asked that question, how do I know that if I should apply the z-score, if I should normalize my data or not? Now, if you see these values, right, straight away should tell you that if you continue with this, you will not succeed, right? Because these data points are actually going to take everything. It's going to take all the credits and ignore these data points, right? So because the distance measure is actually going to find the distance that is existing between each of them. So if you see the distance between 10,000, right, the distance between 10,000 and 7,000, and you compare that distance between 2 and then 3, you can see that these 2 and 3 will not survive. The distance between 2 and 3 is just 1, but the distance between 10,000 and 7,000 is 3,000, right? So you can see this 3,000 will overshadow this one. This one will not be counted, right? Meanwhile, this is actually number of visits and we need it, right? It's actually, that's how it's supposed to be represented. And the information here is very crucial and we need it. But if we leave it like this and begin to build algorithm on this, we will fail totally. Right, so that's what we actually need to take into consideration. We want to actually bring them all to the same scale. So if we use, for example, if we use the z-score, for instance, right? If we apply the z-score on our data, now we can see that all of them are actually on the same scale over here. You can see the data points that we are dealing with right now. Now we don't have one to be outweighing each other, right? We don't have one to be outweighing each other. They are almost all of them on the same scale, right? So now the information that the information that this column is actually going to provide, we will get the information that this column is going to provide us, we are going to get it. The information that each of these columns are going to give us, we are actually going to be able to get it fairly. Okay, so over here, I'm using the pair plot here to get to know the correlation that is existing among the various attributes. In your project too, you're going to do all these, and then I will talk about it. So let me not bring that one here. So if we see the correlation that is existing, actually, the correlation here is very, very low, right? There's not any particular correlation that is existing. We can't actually see any positive or negative correlation that is existing. There's no actually correlation in between them. There's one thing that we can actually gain from this, since this is more like a clustering. It's actually a clustering problem, right? Now, if you see the kernel density estimate here, right? That's the KD. If you're using the pair plot, you can specify that the diagonals should, whatever the diagonals should be, you can specify it yourself. You can make it a histogram, right? If you use a hist here, if you use hist here, it will give you a histogram. Normally, we want KD so that we can actually get to know the densities that we are having here. Now, this one is actually giving you a clue here, right? So that maybe that particular column, right, which is, let me go a bit here and then see, which is the April items, right? It's actually having around 2 clusters in there, right? Which you can actually gain information from. You can actually see these ones too, right? So this is also giving you a clue of how many clusters that you might be getting from these columns, right? You might be getting from these columns. This one is also giving you some clue over here. Okay. So here comes what we are actually waiting for. These are things that we've been doing so far, and this is what we are actually waiting for. So as I said, for hierarchical clustering, we have the divisive, then we have the agglomerative, right? So this agglomerative clustering here, right? You can also use the divisive, right? So if you take this one, we imported this one from sklearn, right? In sklearn, we have cluster there. We can import the agglomerative there. And then over here, we initialize it, right? So normally that's what we do. We initialize it. And then we have some hyperparameters here that you can see. Now, from the hyperparameters in here, right? So this is the same name that you can see over here, the same thing. And then we store everything in a variable core model. Now, if you see the clusters here, we are choosing n equals 3, right? That's the 3 clusters. Last week, we dealt with how to choose this using the elbow method, right? So we could have also done that. Let me just quickly show you so that you remember what we did last week. So for Kmeans over here, going a little bit down. So for K-means over here, instead of choosing any K, we started by giving a range, right? So we could have followed the same steps to do over here. So what I'm doing here is to choose this number of clusters randomly. All right, so I chose 3 over here, and this is coming from the clue that I got from here. Right, there might be at least 2 clusters. So at least 2 clusters, I just intuitively imagine that I can also start from maybe 3 clusters, which will be a little bit sensible. So let's talk about the hyperparameters that we have here. So all these are things that you can actually tune by yourself to get a better accuracy, right? Now, we have affinity equals Euclidean, right? Remember we talked about the distance measures, right? So in this case, we are specifying that this should be Euclidean, right? So remember we also have Manhattan there. We also have the Chebyshev, right? So which we could have used any of them. And then the linkage, right? The linkage over here, we are using average. Now, if we see this one here, remember we talked about average here. Remember we talked about average here. So that's what it's going to do to find the distance between each of these points, right? Find the distance between each of the points. So this and all of them. And then after doing it for all of them, it will find the average of that. So that's what is actually going to happen over here. All right, that's what's actually going to happen over here. So all these are things that you can actually tune by yourself to get the better accuracy that you want, or the better clustering that you're actually intended to do. Then let me move a little bit before I talk about this one. Yeah. So over here, we are creating another column, right? We are creating another column and with the title labels, right? So as you can see over here, then we collect all the labels. We collect all the labels and then store it in that particular column, right? Remember our original data set that we have over here. This is the original data set that we have over here. We have the average spend, we have the number of visits, the April items, food and fruits and vegetables, and the staple items. Then we're creating another one called labels, right? The label is nothing but the clusters, the different clusters. So remember, we specified that we want 3 clusters, right? So it's going to give us 0, 1, and 2 to give us those 3 clusters, right? So it's going to be either in cluster 0, either in cluster 1, or either in cluster 2. So you're going to see zeros, the 0, 1, and then 2 over here, right? So for 3 clusters, okay? So we append that one to our original data sets so that after that we can see those items or those customers that are in cluster 0. So now if we see our original data set over here, let me go a little bit up. This is where we loaded our data set first. Now let's see something before we go to the clustering to see what we did over there. If you see this customer, right, the customer A, this is the customer name. So customer A. So this name could have been any name, right? Maybe it's any name at all, right? It could be any name at all. So this customer spends on average 10,000 per month, right? And then he visits the shop 2 times. And then for April items, he bought one of them. For fruit and fruit and vegetables, just one. For staple, he doesn't even like them, right? And then this customer B, you can see this customer B, 7,000 on average. He spends 7,000 on these items. Number of visits, he goes to the shop 3 times. He doesn't like Apple items, right? So that is 0 over here. But fruit and vegetables, he likes them very much. He bought 10 times, 10 of them. And then for staple items, 9, right? So these are the 2 items that this customer likes the most, right? That's the customer B. For customer C, you can see that the customer C frequently visits the shop, right? But if you see the items that the customer buys, you can see April just 1, fruit and vegetables 3, and then for staple 4. Not that much as compared to customer B that will go even 3 times, but still see the number of items that he or she will be buying, right? If you spot this one too, this customer over here, that's customer E, right? Customer E. Customer E will also come 6 times. And then the items that customer E likes most is fruits and vegetables, right? And staple items. If you see customer G also likes fruit and vegetables most, right? So these customers like fruit and vegetables most. That's customer B, E, and then G, right? B, E, and G. And this customer also likes this item, staple items. All right, so this is something that we can actually spot from here. So customer B is actually at the index 1, right? And then customer E at the index 4, customer G at the index 6. So at a normal circumstance, if we are supposed to do this by hand, maybe we could have grouped these customers, right? Say customer 1, customer 4, customer 6, right? We could have grouped them into one cluster. Then maybe customers who also like maybe Aprils, right? Maybe customer, that would be customer 1, right? Customer 1, and then customer C, customer A, customer C, and then customer D, right? They are the ones that like April items, right? And for them, they buy less of fruit and vegetables. If you can see, they buy less of fruit and vegetables. So manually, we could have put also those customers, right, into one cluster, and then we could have done all of them. So basically, that's what we are doing. This is a small data set, but if you have a huge data set, you cannot do this by hand, and it's even difficult to spot this. Don't forget that we are even visualizing only the first 10, right? If you have a data set with say thousands of rows, then it's going to be difficult to do this by hand. So that's what we actually want to use algorithm to do this, so that it will be more efficient, and even later on we can easily do it without manually doing that, right? So we can spot that difference. Now, if we see this thing that we did and the labels that we have here, we can see that the customers that actually buy, say, fruit and vegetables, right? This one, like fruit and vegetables, this one too, and then this one. Now you can see that their buying pattern is quite similar, right? We have this one that buy four of this. They all buy per items. They all like just buying the same quantity, right? With this one, that's buy a little bit more, but if you can see that it's similar to this customer too, right? So this customer is similar, more similar to that. And then if you move forward, you can see that they all like this one too. So they can group together according to how they behave. If you take it to this, to those that have been clustered into cluster one, you can see that they all like they all like fruits and vegetables, right? You can see they all like fruits and vegetables, and they all like staple items, right? So they've all been grouped into cluster one. All right. So based on what they actually their buying behavior, they've been grouped into similar clusters. Now, if you see these ones over here too, they all don't like a per item. They don't even buy any of them, right? They all have similar behavior. They don't like it. They like a little bit of fruit and vegetables, right? They like a little bit of fruit and vegetables. Most of the items they like the most are staple items, right? They like more of staple items. So they've also been grouped into one cluster. All right. So generally, that's what we actually want to do. That's what we actually want to do over here. So what we did by just doing them this way to see each of them here, we could have just also used the group by, right? Then we group by the labels, right? To see each of the clusters. Over here, we can see the on average, right? Each of the clusters on average, how they spend, right? On average, how they spend. I mean, their monthly spending and how they even buy each of these items on average. We can see that. We can see on average on cluster zero, we can see on average they spend around $7,833, right? Cluster one, on average they spend around $5,166. Cluster two, on average they spend around 2,375. All right, so we can also get an insight from here. And then moving forward, we can
Mr.
now
Ray,
plot.
hello.
Yeah,
Can you change the distance calculations? You have used Euclidean distance, right?
yeah.
If you change it to a cosine or other method, so still, am I able to get the same result, or will this be affect my
So
calculation?
for that, I actually did it, but I actually clean it over down here. I clean it, then I put it there. That's when you get it, you can actually do. So for distance, I left it, but if you can see the method, right? I even changed the method here. If you can see this one, I use different method, right? This is the first one that I use, complete linkage. Then over here I use Word, right? I use Word to build it. So you can actually do that. You can actually, I didn't want to do that for you. I did everything here. Then later on I just cut everything. I just deleted them because I wanted you to actually do that one by yourself.
No problem. No
I
problem.
didn't want to actually do that. For this one, I didn't do it till when I was about to do this because for this word was not here, right? It was not part of this. So I just wanted to show you. That's why I began to do this, to change this one to, because over here I did the complete one, the first one, the average one. So I did not even add this one. I just added this one when I was about to come online, so that you can see that it's possible to change all of them. But I didn't want to actually. So if you want to know how to do it, just search linkage, right? Go to the documentation. You can see all of these metrics that you can actually use, right? And this one too, you can actually tune them. You can even delete all of them and then just use the default ones, right?
Okay. And
Yeah.
how do I decide what are the best parameters for my data set?
Okay, that is something you have to do under hyperparameter tuning. So, for instance, I was using this method, right? I was using this average. Now, for me to know that this thing is working, right? After that, I use this C over here, which is the cophonetic here. Now you can see that here I got 86, right? I mean, I got 0.86. Remember that I said that if you have this getting closer to 1, right? Getting closer to 1. This is 0.86. If it's this one is more closer to 1, so I know that this one that I'm doing is on the right direction. If I did this and I got something like 0.4, know that what I'm doing is not right. I'll go and then change this average to maybe complete and then see, right? Then maybe change this one. Maybe I'll change only this one, right? I'll change only this one first, then see if this will increase. If it doesn't increase, I'll come back, then I'll change this one too, right? So maybe I can change this one to Manhattan. Then I'll see if it will increase. So if it increases, then I know that I'm getting the right hyperparameters, right? Then I'll know that I'm getting the right hyperparameters. That's why later on I wanted to just add this part so that we can see. Now, if you see this 86, we have, I mean, not 86, 0.86, right? Now, if you go a little bit down here, even when I change the average, when I change the average, right? When I change the average, this average to to this complete, right? I still got 0.86 here. Now, when I change it again to word, right, see what I got here. It has started reducing 0.84. You got it. Now, it means that I will not use this method. I will not use this word method here. Right, this word method, I will not use it. I will stick with what I have here. Or maybe I can also, if I want to go a little bit above 0.86, right? I want this one to increase, not to reduce. So I know this is not a good thing. Maybe if I started with this and I got this and I was happy that, oh, I have a good um I have a good hyperparameters here. My parameters are doing well. They're giving me 0.84. If I don't change this word to say to average or to complete, I will be deceiving myself, right? If I started with this one and I had just stick with this or remain with this, I would have done a big mistake by ignoring the fact that or not even getting to know that complete would have boosted it to 0.86, right? 0.2 adding to 0.84 is a big deal. It is a very, very big deal, especially as I always say, if it is a health sector that you're doing this and clustering different patients into different clusters, then it's a big deal. If you cluster a patient who is not having coronavirus into a cluster of patients that are having coronavirus, it's something that is a big error. And it's big error, not as big as you cluster someone who is having coronavirus into a cluster of different people who are not having coronavirus. So if the person is having it and you're saying that the person is not having it, then it's a big deal, right? So for 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 the best practices, try the various hyperparameters, right? Even if you get a high accuracy or high in this case we're using cophonetic, right? So if you even use it and then you get 0.86, you shouldn't stop there. You should change the various hyperparameters. So always for instance, if I'm doing this, I always open the documentation. Then I'll see all the hyperparameters there. Then I'll be changing them. I'll just be tuning these ones and then run it and see. I'll change this one too, and then I'll run it and see, right? Because if you finish and you're going for auditing, if you finish and you're going for the final auditing for them to accept the model, those guys know all this stuff, right? They'll be asking you these questions that might get you stuck because they don't want to risk anything. So they'll be asking all this, why didn't you use complete? Why didn't you use average? Why didn't you use Manhattan? Why are you using Euclidean? They'll be asking you some unnecessary questions that will actually get you confused. But you need to get to know all this. You need to just tune everything, right?
Okay.
Okay, so let me see where we are and then see what. over here. Okay, so we started with average, right? So for average over here, we talked about this is our data set that we are dealing with right now, right? And then for metric, we use Euclidean, which I said you can use any of them. And then we have this average here, which you can change. So the cophonetic, as I said, is so this one is the linkage here is actually going to give us the original distance between the data, our original points, right? Then we are going to find this p dist over here is also actually going to find the distance between each of the points, each of the points, and then measure the distance, right? And get the distance. And then after that, it will measure the correlation that is existing among these two, right? And then give us this, then store that correlation here, right? This the distance will be stored in this one, and then the correlation will be stored in that. So I'm interested in the correlation here. That's why I printed that one out here to see. All right, and then after that, you can plot it. All these are, this one is just setting the figure size over here to be 10. That is the length to be 10. And then the width to be 5 over here, right? So all these are things that you can change to say 15 and 10 or 20 and 5. You can change everything. Setting title, the X label, that is sample index, as you can see down here, and distance, as you can see over here, and then the dendrogram. So there's this dendrogram that you can dendrogram function that you can use to plot this, all right? And all these are hyperparameters. Our z that we calculated the leaf rotation should be 90 degrees, right? And then the color threshold to be 40, leaf font size should be 10. So all these are things that you can actually tune and then see how everything works. So for me, if I get maybe I get a code, right, then I don't understand why this person is using this, why this. So for instance, I'm using leaf rotation here to be 90. If I don't understand, I'll delete this one, or maybe I'll just copy it and then create another cell and then manipulate it, right? So over here, I can say it was originally is 90, right? So I can also change it to maybe to say 45. Then I'll run it again and see what happens. So if I don't know what that particular thing is actually doing, right, I'll just run it again. Now, if I run it again, see what is happening here. You can see the rotation over here, right? You can see how these numbers have been rendered. So I will see that that's the function of what is happening here. Now let me change it to say 180 and see what happens again. Now you can see how the numbers have been turned, right? So now I know the function of this one. Now I know that leaf rotation is the work of the leaf rotation is the is this one, manipulating these numbers, the arrangement of these numbers here, right? So you just play with it. It's nothing dangerous to do. You can just play with it as you want, right? So maybe I can just use 30 and then see what is happening over here, right? See how it is being rendered. So you just play with it. You know, you actually get to know what each of these hyperparameters are doing. All right. And then after that, this is the same thing that we did. The same code that I'm doing here, right, is the same thing that I'm going to do over here. The same thing, right? With exception of the fact that the method instead of average, now I'm using complete, right? So now I'm using complete. That is the point from the last distance, right? From the last distance to the last distance over here, then it will measure the distance between them. So now what I'm using over here. Now I'm using complete over here. All right. Then after that, you can see that it's still 0.86, right? It's still 0.86. Let me spot something. Yeah. Now let's even see something closer. Let's go a little bit closer. Now you can see 0.868, right? 0.868. But this one is giving us 0.860. So it has reduced, right? You can see that it has reduced. Now, when we change it further, right? When we change it further to the word, when we change it further to the changing the method to word, now it is 0.84. That's reduced way further. Now we can see that now the correct method that we should use over here is average, right? It's average. So this is a proof that you actually need to document when you're submitting the final documentation for your model. You actually document all these for them to know that you actually investigated to know that these ones were not working, and that's why you're not actually using it. All right. So the distance that I was talking about over there was this. So if we pick this for instance, right, like 2 and then 3, they meet at this part. So if we want to see the distance between 2 and 3, then we can trace it here to see maybe 1.5. Right? So this is what I was actually drawing when we were dealing with this one. Right, this is what I was actually drawing. This is what I was actually doing over here. Okay. So is there any other question that anyone wants to ask?
Mr. Bait, I have one question.
Okay.
How do I get confirmation from this model that my model is more generalized to the new data?
Your model is
More generalized for the new data.
okay for that um for this kind of a hierarchical classroom, for instance, right? The measure that we actually use to know that what we did is actually the right thing is the cofinatic, right? So if we are actually able to establish a good relationship between the data points that we have here, right? The data points that we have here, then we can actually see that, okay, this will actually generalize on the incoming data. Now, there's another one. Now, since recently we're talking about some of the models that we've built so far, for the situation that we are facing right now, like the COVID-19 situation, most of the models are failing now because what is happening is they were not experiencing the kind of data that we're having right now. So now the models that we built earlier on that were working before this kind of pandemic happened, those models have started giving some errors, right? So which quickly those who are actually quickly spotting them are actually rectifying them. They're actually correcting them. So if you build a model today, just expect it to work to some time. To the some data to the extent of some data, it can give you a good accuracy for some of them, some data that is coming in, but trust me, it will fail one way or the other, right? That's why you always have to be doing evaluations, right? Evaluations and validations and model tuning over and over again. We can say that, okay, we did these different dendrograms, and then we measure the cofinatic, and then we saw that, okay, it's actually working well, right? It's working well. The data points that we have here is actually a representation, and the length or the height of these data points that we have here, right? They're actually a representation of each other. So our clustering over here is actually working. But if this one works on some data coming in, right, it will get to a point that it will fail. So consistently, we need to be keeping on checking over and over again. All right. Unlike like supervised machine learning, where you have a target that you can actually predict and see that, okay, I am predicting this and getting some 98 percent accuracy, right? It's maybe you put these customers together. This customer who is spending this, now this customer has been sacked from the job. He's no more having a job, right? He's jobless now because of the pandemic. Now this customer will not come and spend 4,000 again. All right. So if our model is working here, it doesn't mean that it's going to work um, after this situation. If we built this kind of classroom and we are using for, say, maybe so Amazon built this kind of classroom and then clustered their customers into this kind of classroom, that customers who come and then buy these items and buy these items and buy these items are similar to each other. So when they come to our website, we are going to show them these kind of items with these kind of prices because they have the buying power. They can buy items that are having high prices. Now, after this pandemic, if those customers are no more having their job, they are not going to buy the same thing, which means their behavior has changed, which means the model is no more working. All right. So using the cophonetic, you can see that your model is working, but it will fail one way or the other. So for you to know that it's working, it's just measuring it this way, right? This is one of the easiest way to actually measure to know that it's working. But putting this into production, you need to be training it, or you need to be, evaluating it over and over again from time to time. Else you might be ending up deceiving yourself and your managers that your model is working, your cluster some customers according to how maybe frequent they come to the bank to deposit money, how they pay their borrowed money or something like that. But since now they don't have the job, they might not even have the money to come and pay you. The bank might go in bankruptcy. So you need to actually come back and then tune this model again. You need to adjust this model to the new data set that is actually existing. So most of them are actually using that COVID-19 data set to actually build, based on that, to build new algorithms actually. That's what is actually happening right now. So you can use this to verify, but as time goes on, you need to actually make sure that you're tuning or
Uh,
evaluating this.
Take an example of having a credit card fraud detections, or maybe a mail is a spam or not, or in the COVID-19 cases, the new symptoms on which we can train our model. Okay,
Mm,
so if you think that with the existing features, if we train our model and we put it into production, and then how my model will understand the new kind of a spam or a new kind of a symptoms or new kind of a credit card frauds. So how my model is getting trained by itself.
okay, so let me give a simple example so that you can actually get to understand that one. Now, if you buy a new phone, right? If you buy a new phone, and then you try to type your mom's name on the phone, right? Or let's use your okay. I think your mom's name will be most frequent that you type, or maybe your sister's name or your brother's name, right? Or any of your family members' name. If you type it, if your phone is new, right, you're using WhatsApp and you type it there, right? There will be no suggestions. You have to actually type everything. If you have realized that you have to type everything. But if you use
Correct.
that phone for about a week or two, you realize that as soon as you start typing your mom's name, the name will pop up, and then you can just click on that name, and then automatically, autocorrect will come. If you have realized that, it means that for WhatsApp, they have actually trained the model on several data, right? On several customers' data. So as soon as you start typing, right? It will start to learn, right? Based on its past experience, right? So it's just like you have actually learned a lot of mathematics. Now, if they give you an equation of a line and then they ask you which one is the y-intercept, which one is the constant, you can easily point out to it, right? Because you have seen it before. So in the same way, your model has seen something before, and gradually it keeps on learning from the new data that is coming in, and it keeps on adjusting itself. That's the wonderful thing about this machine learning that the industries are now killing themselves for. Because if you give that same thing for a programmer to program, I don't know how many years or how many lines of code that person will do. And besides, traditional coding is just stuck. If you code, it is just there. It doesn't do anything. But if you do
So
something like
wait, sorry to interrupt you. My question is, uh, I've trained my model with existing data.
mm,
Think that an example of having a mail or a credit card transaction, which is based on my historical data.
yeah,
But what the a new the model, how we can understand for the new
new
credit card
data.
fraud, or maybe uh, a new kind of a spam. How can I block that? How can I how my model can understand that?
So
Because
let's
it has
let's
never
take
seen
the
this sort of fraud,
spam.
right?
Mm-hmm. Let's take the spam for instance, right? Now, if we take the spam for instance, now what Google will do is that if Google is already having several email data over there, right? They have thousands or millions of them, right? And initially when they are building the algorithm, they actually spot those numbers practically, I mean like manually, right? When they were starting building these algorithms. Now they've spotted some kind of keywords. Let's say free gifts, right? Let's say free gifts. Let's say keywords like win, right? Keywords like win. Let's say keywords like cash. Okay. Let's say keywords like maybe gamble, right? Now, what is happening here is that they have already put these keywords, they have already fed the algorithm with these keywords. So the algorithm already knows these keywords, right? Now, if I'm writing an email to you, then my email is starting with this, or is having these keywords inside, right? It's having these keywords inside. For the first time, it will try to warn you, this email looks like a spam. If you have ever experienced that, this email looks like a spam. Now, for the algorithm, right, for the first time, it is trying to learn whether this is a normal communication to you as a human being, or this is one of the spam things that it knows already. Because for the algorithm, free gift is a spam. All right, but the algorithm will actually they actually program it, I mean they actually do it in a way that it actually gives room for this, that it will ask you, right? So if, so more like if this word, right, if this word, and it's the first time, is the first time asked. So as soon as it sees this word, it will ask him, this word or this email looks like a spam. Then it will ask you to mark it as a spam. Now, if you do this, if you mark this as a spam, next time it will not ask you again. As soon as it sees this word, it's spam, it goes straight to the spam folder. It means that it has learned from its mistake. It will not come and ask you again. You get it? So
Yeah, I got it.
gradually, it is learning from you, it is learning from its past mistakes. That's why we don't only use this machine learning, but we also use the deep learning concept, because this will actually come under deep learning. Mostly, it learns like the neuron in your own head, right? Like that you can actually ask your mom that this person looks like someone who can cause maybe he said he looks like a thief. Then your mom will say that no, this guy is not a thief, because your mom is having more experience than you have, right? Then your mom will tell you that it's not a thief. So next time if you see him, you change your mentality that this guy is not a thief. Or maybe you play with some guy, your mom will advise you, don't play with this guy again. I don't like his behavior. Then you stop playing with that guy. So that's how it actually learns, right? So as soon as we grant it permission that it looks like a spam, it has learned from it automatically. Next time when an email comes like that, it will push it straight to the spam folder.
Got it. So now that how my model is taking the input, like this marking is that this particular keyword is a spam
Yeah.
from an end user.
Mhm.
How the model is taking that input and getting updated, where it will happen in a production server.
Okay. For this one, for the model to actually classify this one as spam or not spam will not actually be something that you can actually ever see. It's like I don't know if you know anything about Flask, or if you know anything about Heirarchical.
Yeah, Zango also, Zango
Yeah,
Flask,
yeah.
Heroku.
So if you're doing something like that, I think even when we're doing the I think it's the Kmeans classroom last week. If you remember, we're using a certain window.
Correct, correct, correct.
Yeah, yeah. So we just put number of clusters that we want, say 5, and then it will give us the 5 clusters over there. All right. So if you remember, that was a code that I was already having. I was having the code separately, right? Then the code will pop up this window for me. Then I'll just put it over there. So this is something that Google is having. Whatever you send, whatever email you send, it passes through Google before it comes to you. So if I am here, right, I'm sitting here and you are sitting here, and I'm sending you an email, it will not come to you straight. It will go here. It will go to Google before it comes to you. It's
Okay.
like you are going to Google search bar or console or whatever they call it, and then you are searching for, say, data science courses in India, right? If you search this query is actually is something that you are sending, right? It's something you are sending to Google servers to actually render it back to you. So before you search this one time, the next time you start typing D, they will start telling you, they will start completing it for you, data science, right? Because it has learned from you. So this one
Okay.
is something sitting somewhere, but it has already learned, right? So that's why people raise a lot of concern about Google Chrome itself. It's having a lot of algorithm that can learn from you automatically that you might not even. I don't know if you have even seen the recent allege against Facebook that now they can that messenger itself that they have is actually stealing most of the information that you have, right? And they are using them for some marketing stuff that you might not even be interested in, but they still be targeting you with those marketing stuff because that's where they make money out of, right? And I think this guy, this I don't know if any of you know about this that go guys. I hope you've heard about this guys that go.
Is ethical hacker or what?
I did not get you.
Is it he's an ethical hacker or
No, duck go. It's also like Google.
okay?
The same is the same like Google, right? So you can also search anything on internet with this. But for Google, it will learn from you. Google is having millions of algorithms that can learn different things from you that you might not even know, right? But DataGo is saying that for them they don't learn anything. According to them, that is according to them. So they say that they don't store your information. That it's like you're using incognito mode, right? They say they don't learn
Mm.
anything from you, but for Google, even if you use I mean, for Chrome, for instance, if you use, even if you use incognito mode, they still trace you. So, I mean, they have millions of algorithms, and the algorithm is just at their end. That's whatever you do pass through their end before you receive your whatever you have to receive back, right? So automatically it will learn from you.
Can't we encrypt our models for the
Okay,
safety purpose?
there are some things that they will ask you to do that mostly we don't do. That they will ask you if you use the Chrome, right? There are a lot of settings that you can do. The problem is that there are some of the things that if you switch them off when you search, there are some results that you might not even see, right? So they use that to their advantage. And some of the settings, even where they have placed it in Google Chrome, most of the people don't even know. But you can. There's a way that you can do it. I've forgotten the name, but there's a particular company that actually does that. That you can easily install their software, and you can block Google from actually learning from you. But how sure would you be that those guys that you're even installing their software are not also learning from you? Because this AI and machine learning stuff has made things a bit unclear, has made things a bit difficult. So is quite, I mean, fancy, but that's the world that we are living now. So it's better you have knowledge about how things are moving instead of being part of the mass that you don't actually know what is going on. So I just want to show you this one before we drop off. Let me see. Okay, so as I said, the project that I will load, I have not loaded a project for this, for Kmeans and then for hierarchical classroom. So for that, if you guys want me to do that, I can give individual projects for these ones, right? What I'm thinking is that the project that I will give you will encompass most of the algorithms here that um, you'll be actually need most of the algorithms to put them together to get to the final production. So what I'm going to do is to actually load a project which you will need to do dimension reduction or PCA on that before you can actually solve it. Because if you go straight away to solve it, you might end up um, confusing yourself. You yourself will be frustrated because of the variables. Now, this is one of the things that I want to show you. Now, look at this data carefully here. I have this vehicle.csv data that you're seeing on my screen. All right. Now, if you see this data, right, we have this. Let me see if I checked. Okay, is there? Okay, I think I even have another one that I want to show you. Not this one. Okay, yeah, I think this one will work. Okay, now see this data that we are having here. All right. Let me zoom in a little bit. Now, all these are the column names that you can have over here. These column names are the ones that are fetched here: ID, diagnosis, radius mean, tester mean, perimeter mean, area mean, all the way to the last one, fractal dimension worst, right? So we have over 32 features over here. We have over 32 features here. Now, what happens is that if you use this kind of data set, if you move on to build algorithm on these data sets, you yourself might end up having a difficulty in coming into conclusion with anything over here. What normally we want to do is to, okay, so normally we'll be having, oh, come on, my pen is actually disturbing me here. Okay, let me get rid of this and see. Okay. So normally we'll be having this, then we will be putting some data points in here and then try to work with this. Maybe we can put a line here, some regression line here, and then maybe some new data set will come. We can actually make some predictions. Now, this one is a two-dimensional space, right? Say X1 here, X2 here. I'm not using Y or X, I'm using X1, X2 here. So X1, X2 is nothing but this. It could be any of the column names. Maybe X1 is say the diagnosis, X2 will be say the radius mean or whatever it could be, right? Now we have 32 column names or 32 dimensions that we are dealing with. This is two dimensions. Now, if you have 32 dimensions, just imagine how you will draw this or how you visualize this. Maybe you have another one here, you have another one here, you have another one here, something like this. You have to do that for 32 times, right? So if you want to visualize this, it should be like that, 32 times, 32 times, right? So you might end up with something messy like that. All right. So what actually naturally we want to do is to reduce this 32 to a two-dimensional space, right? What we want to do is to reduce this 32 to a two-dimensional, not strictly a two-dimensional space, but I mean, since it's actually easier to visualize this in a two-dimensional space, we want to actually reduce this 32 to two-dimensional space, right? The idea here is that let's say you want to predict let's say GDP. All right, let's say you want to predict say GDP of a country. Now, if you consider GDP of a country, there are several factors that you might consider. Maybe you can say the workforce may contribute to the GDP, maybe some innovations that is going on in the country might contribute to the GDP. Maybe the current situation, right? The current COVID-19 might contribute to the GDP of the country. Maybe the infrastructure the country is having might contribute to the GDP. You might end up with maybe about 50 items. Now, what we will do finally is to actually look at all the 50 items that you might come up with, right? And then see that, okay, this one is more important. Maybe the workforce is more important. Maybe the COVID-19 situation is actually affecting the economy, so it's more important. Maybe the infrastructure, right? If the health system is quite good, we can actually improve our economy. If we actually outsource most of our softwares to countries like the US or Canada or Australia or something like that, we can actually boost the economy. So you might end up picking some of the items, and you might end up dropping some of the items, right, that are not important. So that's basically what you actually do. Now, if you drop an item here, maybe you drop, say, the education system. Maybe you say the education system is not important, so you dropped it, right? So if some way, somehow, the education system is contributing to the GDP, right, you have lost that information. Okay, you have lost that information. Now, what you don't want to do is to lose information based on the features that you have. You don't want to lose any of the information. So what you can actually do is to that. So you have two options here. All right, you have two options here. One is called the feature feature elimination, right? One is called feature elimination. One is called feature selection. All right, one is called feature elimination, one is called feature selection. Now, let me see if I can just do it here so that it will be a bit clear, right? So I said one is called feature elimination. That is dropping some of the columns that you think that is not important, right? And then one is called feature selection. So if you take feature elimination, for instance, maybe as I list a lot of features that you can use, you can say education is not important, so I'm dropping that, right? I'm eliminating it, right? So if you use the feature elimination formula, then you can eliminate that, right? Now, what actually normally works very well, right, is what is called the feature selection, right? And for feature selection, one method that actually works very well in feature selection is what is called the PCA, or the principal component, right? Is the principal component. Now, what principal component does is for all the data points, right? So let me just pick this data point. So for all these data points, let's say these ones were all the way up to 32. So x32 here, right? X32 here, just like we were having in our data sets, right? We're having 32 here. So I'm just saying that all these features are just the column names, right? All right, so maybe diagnosis, maybe let me see some of the features there. Radius, mean, texture, perimeter. All right, so these are the column names all the way to 32. Now, if I drop this column, right, if I say this column is not important, then I'll drop it. I lose the information that this column is going to give me, right? That's the feature elimination, right? If I drop it, it means that I'm performing the feature elimination column. Now, what I can also do is the feature extraction, right? Which in feature extraction, one of the important um, formulas that you can actually use to do that is the principal component, right? Is the principal component. Now, what principal components will do is that instead of dropping these columns, it will find a way. It will find a way to combine some of the columns. So we have 32 columns here. So maybe fetch some information from here. Let me use this. Maybe fetch some information from x1, then fetch some from s2, right? Combine them. Maybe fetch some from s3, combine them. Fetch some from x1, combine them, and then call them one feature. Maybe we can call them, say, M, right? We can call it M, and then maybe do again for the other features. Maybe x2, I mean maybe x5, right? x5, x7, x8, x9. Maybe combine all of them and then call them N, all right? And then do the same thing. It will do the same thing for all the features that we have here. It will extract them. Now, the beautiful thing about this principal component is that it will do this linearly. So, for example, it can do, say M here, right? So it will combine some of this. It will find a way to combine it. So maybe it will do, say, 2 times, or maybe 0 point. I'm just choosing any number randomly. Maybe 0.5 times x1 plus maybe 7 times s2, right? Plus, say, maybe 0.04 times say x7, something like that, right? Plus whatever you can add. Then it will combine these features, right? Extract information from these features and then store it in another variable called m, right? It will do the same thing for the other features, right? Maybe it can do maybe 10 times x11 plus, or maybe minus 14 times x8 or something like that, right? Plus something like that. It will just find a way to do that, to extract information from all the other data points and then store it in another variable. Now you'll be left with these two variables, right? So this variable will be called principal component, right? This will be called principal component. Okay, so we will extract information from all these 32 that we have over here, all these 32 features that we have here, the radius, mean, texture, all the way to the last one, fractal dimension, worst, right? That's what it will actually do. Now, one good advantage of this one again, let me go a little bit down and then show you something. Now, if you see this one here, right? If you see the correlation here, you can see, let me spot some of them. Let me spot some of them and then show you, let me use green or maybe blue will work better. So now let's see this one here. You can see some of the correlation 0.09, almost 1, right? Very high correlation, right? Very, very high, right? Very, 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 very high. It's some here 0.82, right? Even if you spot some of the negative ones, let me see if I'll get some of the negative ones. Let me see. We have 0.28 negative correlation here.
Perimeter mean 0.97.
You said, what do we mean by? Can you ask your question again?
There's a perimeter mean column have got a higher correlation, 0.97.
0.97. I cannot spot it. If you can show, let me know what it is.
It's a perimeter mean.
Perimeter
This
mean.
there's a radius mean
Okay, radius
0.9
texture mean, perimeter mean.
to right. It's 0.97 there.
0.999 is here. Okay, should
Yes.
I go like that?
Last per
Okay,
second.
okay, here, right? This is one you're talking about, right?
Yes, yes, yes.
Okay, let me do it this way so that you can see what that means. Let me go a little bit like this. Let me go a little bit. I want to make it a little bit small so that I can trace it for you to see. I think I made the size way too big. Okay, so this is the 0.97. Let me trace it. So if you trace it down, right, I'm going to write it up, but if you trace it down, this is the perimeter, this is the 0.97, right? If we trace it down, if we go a little bit down, is the perimeter west, right? Perimeter west. So I'm just going to write it up here so that we can actually talk about it. So let me zoom it again and then write it over here. Okay, so it's this one. Is this one, right? So that was perimeter west. Okay, so it's perimeter west. Let me pick this. Yeah. So I'm going to trace that so that you know what is happening over here. Perimeter west, and then this. Okay. So now what is happening here is that this is a correlation that is existing between this value, this feature. Let me change this. Between this feature, perimeter mean, and then perimeter worst, right? So what is saying that they have these two features, right, have high correlation, right? Very high positive correlation, right? So what is the problem here? The problem here is that if these two features are having a high correlation as high as 0.97, right, which is almost closer to 1, right, which is almost if you want to approximate it, then it's almost approximately 1, right? Now what it's saying is that the information that parameter west will give you, right? The information that parameter west will give you, the same information parameter mean can give you, right? So these two informations are almost the same thing. They're almost giving you the same information. So what is the point of keeping these two values and then confusing your model, right? So what you can do is to actually drop them, or I mean drop one of them and then use one of them, since they are all giving you the same information, right? You can drop one of them and then use one of them since they're all giving you the same information. Now, don't forget, it is, although the correlation here is 0.97, but it's not 1. It means that there's still 0.03 left. All right, so this is still a small information that maybe one of them is holding that can still help you make some decision somewhere. Now, if you drop one of them, you have lost this information completely. If you drop this one of them, you have lost this information, this small information, right, which might actually help you to build a better model. That's why PCA is quite popular here. So what it will do is that with these features that are actually high correlation, correlated like that, it will combine these features, right, and then create another feature out of them, which will hold information of both of them without losing it. Principal component does not grant 100% information, right? That it's going to hold the information here 100% and going to hold some information here 100%. It will by all means lose some of the information during the extraction, but still it is better than dropping it. All right, that's why principal components will actually help here. And after applying principal component on this data set, you will not see these high correlations as you're seeing over here. 0.94, 0.99, you will not see such over here. All right, if you apply this on that. I think I even have a data set that I did something like that, but let's now. So if you do them individually, right? If you see the features individually, you can see the correlation that we plotted here. You can see as straight as possible. So this is a very strong positive correlation. This is correlation between the radius west, right? Radius west and perimeter mean, and then radius west and area mean, right? You can see the correlation is very, very high, very, very, very high positive correlation over here. And this will actually run you into a trouble, right? Something they call multicollinearity, right? Which means that multiple of the variables are actually correlated. And it's actually going to give you a trouble because they're all giving you the same information. So why continuously keeping them over there? All right, so the best way to do is to actually extract these informations. All right, so as you can see, if you see, for example, radio west and area west, very, very, very strong, very, very, very strong. All right, so this I hint for you not to do it. Some are even negative, although it's not that strong as the positive correlation, but some are still correlated negatively, and some are also not giving any information. Are not correlated with each other. So for them, they are okay, but for these ones, for these variables, you need to be very careful with them. All right. If you want to see all of them together, you can also use the pair plot to do that. Then after that, you actually need to write your insights, right? I'm not giving you the same data set. This is an example, and I mean, you will follow same process to do it. So I'm giving you an example of that. And some outliers might also exist, which if you want to consider that, you can actually take a look at it and then see how you can actually deal with those outliers also. All right. Then after that, you write your final insights over there. So and some of the algorithm in this way, I did not, in this one, for instance, I did not actually add build algorithm on this. I did not add that part to it. All right. But with the problem that you actually going to have, there is supposed to be a combination of some of the algorithms that we have talked about so far. All right. Someone is saying that voice is not clear. Guys, can you hear me?
No, you're audible.
Oh, okay, okay. So maybe I think it's a network from your end, something like that. So that's basically the things that you have to do. I think after here you can continue from here and then do the algorithms. I mean, start to build your own algorithms and the particular algorithm that you need to know. Now, what you actually need to first know is whether the problem is a classification problem, it's a regression problem, or it's kind of clustering, right? So for that, you need to first figure that one out first. Now, after figuring that one out, if you figure out that if it's, for example, if it is a classification problem, then you need to know which classification algorithm is going to help, right? The best thing is to build a lot of them and then measure the accuracy and then see how each of them is doing, right? And then with the most important here is to check the hyperparameters. So if I am the one doing it, for instance, I'll make sure my documentation is open. I see all the hyperparameters in that. I'll keep on tuning them, mess them up, and then correct them. All right. There's no harm in changing them and getting errors and going back and doing it. That's the only thing, the only way that you can actually get to know it and get to learn it. All right. And the other thing too, if you do your research and then you see some of solution that someone has actually provided, maybe on Kaggle or maybe on some other platform, right? The good thing that you can do is to actually study what the person is doing, right? And then know why the person did it. Because if you are submitting it, you cannot just put it there because on Kaggle or on the other platform, they just put the notebook there without explanation of how they did it, and you cannot go and ask them, right? You don't even know who put it there. They just put it there. You don't actually know why the person did that, right? So if you pick, say, for instance, if I have given you this and over here, I'm doing this right now. For me writing this code, I know why I did it, right? So if you are doing it, you should know why you did it, and after that, you should provide your insights about that, right? That's because this one will mean nothing to the people you're submitting to. These ones will mean nothing to them. The only thing that they can read is the comments that you can write over here. Right? That's the only thing they can read to get to understand what is going on here. This is the one that you know. They don't know about it and they are not even ready to know about it. Right? That will be your own problem to actually get to communicate it. And one important thing, if you're submitting your notebook, right, make sure that the question, let me see if I have something like that. I don't know if I put something like that. Okay, maybe here I wrote something. So make sure that over here at the top here, you write the problem statement and what you're doing and how you're going to do it, right? You write it over there and then you put that documentation over here because that's the first thing. That's the most important thing. If you submit this notebook or a link of it to your GitHub and you apply for any job, they click on that link and go and see it. The first thing they need to read and understand what you're doing is the introduction that you give here or the background of the problem that you give here. All right, to understand if you start with a code like this, they just see it and then just close it because this one will mean nothing to the HR person who has studied some HR concept in his or her MBA time. This thing they are plotting will mean nothing to her or to him. They don't actually know anything about this and they are not ready to know it. The only thing they can read is what you put here, right? So maybe this problem is about this, and this is how I intend to solve it, and this is the final outcome I intend to achieve, right? Then finally you write your conclusion over there, right? And if you want to, I mean, be a kind person, you can also be providing comments, right? Just like whatever you're doing, you provide some comments in there, right? So that that will also help you, and then help those who will also take your notebook next time. All right, so that's some of the some best practices that you can actually take into consideration, which is very important, very important. If you're submitting your notebook, especially if on the real world, if you're submitting your results, we don't actually submit notebook or your PyCharm or whatever you are using to build whatever you're doing. You don't submit it that one. It's actually unnecessary, and they don't actually want to know that. All they want to know is your visualizations, right? Maybe you just like this one, for instance. If you want to put let me go back here to the piece. Yeah, maybe you put something like this, right? Now this one, what does it mean? Some of them, trust me, they even hate mathematics. As soon as they see this, they remember their mathematics days that they were failing mathematics.
It's 11 o'clock.
They actually get angry with you right there. All right. So what you can do is actually make it more convenient for them to actually understand what you're doing. All right. So if my computer is saying it's 11 o'clock, I think we can end here. If there's any question that you can ask, and anyone can ask, so that um otherwise we can end it here.
Is there any bias and variance trade-off kind of a thing in hierarchical clustering?
Bias trade-off.
Yes.
Okay, in hierarchical clustering, we don't actually do bias trade-off, unlike what's earlier on we were doing. You just even reminded me. I was thinking of us having one class on this kind of model of evaluation and stuff like that. I don't know if that's time we can actually have it based on how we do the project. There's something I was even thinking of a pipeline, maybe one class on that one. Maybe. So in hierarchical clustering, yeah, it's actually not that much considered over here. The main thing over here is to make sure that whatever you're clustering and the cluster that you're having, right? The actual distance that you're using to measure the clusters, right? Actually as close as possible to the dendrogram distance that you have, all right? As close as possible. It's like you build KNN algorithm, and then you use the various validation measures to actually validate it, and then you see the accuracy, and then if it's high, then you can see that what the model you did is, I mean, if it's high on the test data, that one needs to be clear, even if it is high on validation data or on training data, is actually not something you should even consider in the first place. All right. So if there's any other question, we can continue with it.
Hello,
Yes, I can hear you.
can I ask a question in different context? And I just want to know that how software engineering is different from data science, and if someone is really interested in
Can you make your voice a bit louder so that I can actually hear you?
hello,
Yes.
so
Yeah, I think it's better now.
my question is how software engineering is different. Means web developing and software engineering is different from data science, and if a guy is doing something in web developing and something else, then how you can switch that? Like I'm right now taking your classes for few months, and it is very hard for me to grasp all these concepts in a means in a day-to-day basis, because I have been working something else that is not related to these statistics and mathematics and all.
Mm.
So if I want to convert my career from that web developing or from front-end software developer to data science, so what would be the basic criteria to do that, and how can I make this transition? And after doing all these projects, because I have not yet done any single project because of the time limitation and constraint, and I've been working for Monday to Saturday, and then I only get free day for Saturday Sunday. So if I able to do all the projects you have given to me, uh, how can I make this transition? Because I don't have currently no guidance regarding that.
Okay, so there was this kind of conference of this there was a person who is also doing MBA, and the person also asked the same question. And there's this guy who also is a software engineer at YPro, and then he was also talking about the same thing, that he has been doing software engineering, like the back end and the front end, for some time, but now he wants to actually switch to data science. He doesn't know if it is the right thing or so. For me, if you ask me that personally, right, what I would ask you is, what I would say is that I don't actually understand why software engineers are actually delaying, right, in switching to data science. So if someone who is doing philosophy, right, has switched to do data science and is a data scientist right now, then you doing software engineering, why are you still waiting? Because trust me, with some time to come, the web development, the front end and the back end itself is actually going to be done by this kind of AI things. All right. So if you know, what is going to help you is the domain knowledge that you have right now. Now, if I finish building this thing in the notebook, right, what I need is to deploy this. And to deploy this, I need this kind of software engineering skills to actually do this, right? Not into details as they will be coding within C and the C++ and the kind of Java and stuff like that. But trust me, if you already know a little bit of web development, or you know a little bit of software development, you have an upper hand in just switching into this, right? You just need some one or two steps, so one or two guidelines to actually step into this. Okay, because everything that we are doing here is just in line with that. It's just different. I mean, different terms that we are using, but it's just in the same domain as software engineering. If we take say Amazon SageMaker for instance, right? Previously they were using it. It was just part of cloud computing, right? And those who were doing software engineering were already doing all those things already. So just recently that they started adding those deep learning to it, right? So if you're already into that, if you're already into software development, it's easier for you to actually grab this concept easier than any other person from any other field, right? Easier than even someone who has done statistics or whatever. It's actually because if you take statistics for instance, which of them have we worked when we are building the algorithm? We don't actually even work a single one of them, right? The only thing that we need to know is the concept behind it. And after that, everything comes back to software engineering. So if you know a bit of software engineering, you have like 80% upper hand than any other person coming from any other field. Because if you're coming from any other field, you will learn it, but not as easier as someone who's already into the field, right? That's why sometimes, even if you're applying for the job, they will ask you if you have programming knowledge. Maybe they will not even specify that Python or whatever, because they know that if you have a little bit of programming knowledge, you can easily grasp these things, right? For instance, for these two ones that I'm doing over here, if it is Java or Python, I don't know how many lines of code that I'll be writing. So if you're able to be writing those kind of things, especially JavaScript, for instance, even doing those kinds, for instance, then I mean for some time, then import just from scikit-learn.cluster, you import these things, and trust me, These ones were built with C and C++. All these are libraries that we're doing, right? Were software engineers who were building it. We are just using the surface here, but everything has been built from scratch from these software engineers, right? So if you have a
Mm.
knowledge in software engineering, you have a high chance of doing this. What is helping the other field, which is, I mean, like those coming from the MBA background or those coming from, say, law background or from some background that you may not even be thinking that they will be doing data science, but they are still doing it. It's domain knowledge. All right, so that should be one of the weapons that you should hold. So if you have software engineering background, for instance, that's a huge plus to easily switch. You just need one or two guidelines that learn this from this, learn this from this, learn that. Then that's all. But not like if someone is coming from MBA or philosophy background, for instance, right? That person needs to do more work than you are already doing, than you um, coming from web development or software background. You just need one or two steps to just get there.
Okay.
Yeah, so it's just that there's a lot of information online. There's a lot of courses. There's a lot of everything. If you want anything, you can easily get it anything. So that's one of the confusion out there, right? That um, you don't actually get to know the step-by-step way of getting to it. And if you don't actually take your time to do this, it can actually take you a lot of time too. That's one thing about this AI stuff. It can actually get you, especially when you get to the deep learning and the machine learning is, I mean, this part of the machine learning is just I mean, kind of easier and I mean easy to get, right? But if you get to the machine and the deep learning part and the NLP and neural networks part, right? That's you need to be very careful because those things are sensitive and it's actually help you to build better machine learning algorithm. All right. So if you're coming from software background, trust me, you have an 80% upper hand in this background. The guy that when I was started with this data science career that I learned from, right? The guy was, I mean, he is working at IBM in the USA, right? But he came from philosophy background and then started learning this and then became a data scientist at IBM. All right.
Okay.
So if that person was able to do it, I mean, you coming from software background, you don't you don't actually have any
I,
excuse.
I'm not a software background actually. I was learning that web developer and all these things under any means in like online based course. So that is why I thought at that time that to join any data science or ML courses. But
Yeah, because from here, if I want to deploy this, I will be using Flask or Heirarchical or something like that, right, to do it. And they are all part of this web development stuff. They are all in that arena.
okay.
Mhm.
So building the knowledge in data structures and algorithm will be also helpful for data scientists.
Yeah. Actually, if you're going for a startup like that, they don't actually care. They will not even ask those kind of questions. But if you're going for a company like um I mean, a multi-million company like Google or Microsoft or something like that, they will be asking you those questions if you know
Okay.
your data structures. So,
Because I'm novice to coding and all that. So I thought my field like I have to code well, otherwise I will not be surviving this
yeah, but
industry.
if it comes to machine learning and stuff, that's why this part has actually becomes that's kind of important because we don't actually code as in code as you'll be doing in JavaScript or those kind of languages that you explicitly be coding to do this, right? This one you don't actually code. Like we just did this one, the cluster it, we are done. Now, if we get a new data set, you are not the one going to do it again. It will do it by itself. What you have to do is to watch over, make sure that everything is working, right? So we don't actually code like we are coding to. I mean, not like those traditional languages like those Java and JavaScript and stuff like that. So if you have been able to learn those languages, then trust me, this one is easier. That's why Python came and people just jump on Python like that because the
Yeah,
traditional.
I felt JavaScript is little harder, tough than Python. Python is
Yeah. Python is just, it will just obey what you write. That's all. So if you write, whatever command you write is what it's going to do. Unlike like Java, for instance, it has to follow certain format. I mean, some strict formats. If you mess up the syntax, everything is gone. This one, if the way you write it is how it will behave. So it gives you more flexibility to actually learn as a user, right? From as you as a person, it makes you actually do what you actually want. It gives you that kind of freedom. I think Sanjay wants to ask question too.
I have one question. Uh, I want to have a complete list of machine learning algorithms so that I can learn deeply on the techniques.
Okay, like you want a deep insight into machine learning algorithms.
I want to have a complete list of algorithms, like, in linear regression, there are methods called OLS, GLM, lasso regression, and ridge regression, some detailed kind of a thing where I can more focus on that.
Okay. Maybe I can put some compilation on that for you. Maybe that will help. Maybe I can put something together like that for you.
That will be of great help.
Yeah, 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 yeah. Maybe that will actually help. Now, one thing about this machine learning stuff is that when you learn machine learning to this extent, right? Um, for me, I will consider it as let's say if the steps are 10, right? I'll say this step is actually at the third level, right? Maybe you're at the step 3. Okay. If you really want to get into this data scientist kind of thing, right? Then you need to actually get into deep learning, right? That's the neural networks and those NLPs and stuff like that. Right? Because with even what is actually happening over here is that the world is actually getting simpler and simpler, and those who are actually doing the thing will actually make it more complicated and complicated, but the surface of it is simple and simple. Like you just say, Alexa, what is the weather today? Alexa will tell you. But those who are learning it, it's actually getting complicated and complicated because there are some people sitting somewhere who are always doing research and keeping on bringing stuff, right? For instance, if you take Harvard for instance, Harvard just sat down, do some research, and brought their own library, right? There's a Harvard library there that you can actually use. They just, some people in Silicon Valley, for instance, that's their lifetime thing they've dedicated themselves to. So before you finish learning, say, support vector machine, they will come up with something that will do 100 times support vector machine will do. And you are going for a job, they will ask you, do you know this? And then you get stuck. All right. But you cannot get everything at once. You need to start from somewhere. All right. So the best thing that will actually help you is to not stop here, but move one more step to deep learning. Right. If you can grab deep learning, you are in this data science and this AI domain. You are there, right? And if you get the right step by step to get it right, you will not actually take time. But if you don't actually get someone to guide you, or you don't actually get the right steps, it might take a little bit of time, right?
Because this AI and neural networks kind of a thing, which are more costlier comparable to ML, if I'm very correct.
They are what?
They are a bit costlier to
Yeah.
implement.
Now what is happening is that if you take software for instance, right? Earlier on, if we have if we have a software that we have written, maybe in Java or C++ or whatever they have written it, that software costs so much, so high. If you remember the SAP time, those times, even a single SAP, it costs millions of dollars. Now, because of AI and machine learning and this kind of deep learning stuff, those software's price are coming down. Now, what is going up is education. education in that field. I mean, in this kind of AI and machine learning. Now, one of my friends who is in the US and doing this AI stuff, he pays $53,000 per year, right? $53,000. Now, if you convert this one to rupees, right, it's not a small money. But right from 2015, 16, there were no courses like that. So even if you search online, maybe you might find some one or two schools that are even giving some online tutorials on that, which were not that popular. But right now there are universities that are put in a whole course, maybe MTech in data science or MTech in machine learning or something like that. And that's where they're actually raising the price. Even if you see the postgraduate programs, right? The price are very high. If you check those postgraduate programs that have been offered, the price are going high and high because the demand over there is actually very high, very high. Now, what is actually making that happen is that if you are able to invest in yourself in that field and you get into the company, right? You just become the engine of the company right now. Because all the things, if I don't know if you know about automation anywhere. Now, what is happening is that most of the things that people are doing manually are being automated, right? If you can automate my customer care for me, right? I will not be paying any person to sit there and do those customer care stuff. It will be automatically a bot, right? You just create a bot that will be doing all those things. Now PayPal doesn't do customer care as they used to do, that you have a customer care line, you can call and stuff like that. It doesn't happen again. Everything is bot. So if you can create that for me, right? I'll know you've cut my cost to about, I mean, more than half of the cost that I'll be paying. So I'll value you as an AI engineer or as a machine learning engineer or data scientist more than any worker that I have. Because with you alone, I can get rid of about 5 employees, right? The work that you do will help me get rid of about 5 employees, which that money can actually help me scale other sessions of my work. Right. So for companies, they know the importance of this, right? That's why in the US it has, I mean, starting from 20, I think from 2003 all the way to 2020, all the way, it's going to go beyond that. Data scientists have been the #1 job, or because they know the importance of them, right? For instance, for you to investigate, if you take healthcare for instance, for you to do a research and then come up with a explicit drug, or maybe a prescription that this drug has worked on maybe about thousand patients, it's likely that it's going to work on these patients too, right? It's actually a whole lot of team and research engineers that will sit down and do this for a number of maybe about 4 or 5 years before they will come up with their results. Now with this AI, right, with if we take NVIDIA for instance, NVIDIA does those kind of research. Now within say a week, or within as most as a month, they can actually do that kind of job that were earlier on taking them about 3 or 5 years to do that kind of research. They can do that analysis, right? That's we're taking people 2 or 3 years. So what do you think these sectors will actually value data scientists or machine learning engineers or deep learning engineers? They are actually valued as precious as you can think of. Right, so it's actually sensitive, and although there's a negative side of AI and stuff like that, but if you think about how this thing is going and how things are changing as rapid as possible, it will get to a time that even if you go to a law school and you don't know this kind of a little bit of machine learning, it's going to be difficult to even get a client. Now they even have this company. There's a private company that does that. It analyzes all the cases that in court, right, that has happened in court. So if you're a lawyer, you have a case that you're going to do in the next day, you can see those cases that happened previously. Like if you're a lawyer in India, for instance, you can study all the cases that has happened in the US, in the Germany, in Australia. You can see all those cases, gather your evidence, and then just go and win the case. As simple as that, right? Unlike at first, you have to be going to some libraries, some online research. That information you cannot even find. But with this, they have a whole database that with just a click, you can just get those information. All right. So
Uh,
that's what is happening.
when do we use deep learning algorithms? When we already have a machine learning algorithms which are much more efficient. So why do we go with deep learning? Is
Okay.
it
So
the
what
cost is
is
the only impact, or is there any other
yeah,
mismatches?
what is actually happening is that deep learning is not different from machine learning. They are all the same thing. It's just something that makes it work faster. All right. For
But
instance,
that requires GPUs, right?
yeah. You can, like most of the things you cannot do in Jupyter Notebook like this. Most of the things you cannot be doing it. Your system will even crash. It will not even work.
It's true.
Right? Yeah, that's why Google came up with Google Collabs, because Google Collabs you can actually set GPU there, right? You can actually do that over there with Jupyter, ordinary Jupyter notebook, or with your system like that. It's going to be difficult. And PyCharm is also a good thing to actually use. Now, if you take logistic regression, for instance, right? We already use logistic regression in machine learning. All right. Now, in logistic regression, what actually we use is the sigmoid function, right? Anything that looks like S, right? Any function that will help us to plot something like X, which will help us to actually get our range from 0 to 1, right? To range between 0 to 1 is what this sigmoid will actually help us to do. Now, if you go to deep learning, the same thing is there. The same thing is there. Now, what has actually changed is that instead of um, logistic regression, we have something we call the ReLU, right? That you're going to use. Now, instead of ranging from 0 to 1, now we are going to range from -1 to +1. All right. Now, this is a research that people sat down and did about this logistic regression and this sigmoid curve that we use. But this function, this real function, there are some other, of course, that we can also use, right? There's even TAN-H that you can also use, which also works well. But mostly, if you go to deep learning, instead of logistic regression, the sigmoid curve, right? You'll be using ReLU, right? You'll be using ReLU over there. Now, what this one is actually doing is that it's actually converting this one, right? Instead of being in sigmoid form like this, right? It will just go straight like that, and then getting to that part, it will just cross this X bar and then go straight again, all right? But it is still within 1 and then -1 over there. It is just a modification of this one. So uh, modifying this sigmoid curve, right? Modifying this sigmoid curve and using ReLU is actually helping us to make this function more effective, right? So if you take machine learning, for instance, right, we see that machine learning here, we have deep learning here, right? So deep learning is actually under machine learning. Okay, so it's it means over here is that whatever we are doing in deep learning is already there in machine learning, but we are adding something on top of it, right? This one is just like something that is helping us to work faster. Just like we already have Java, we already have Java, we have C++, we're doing our traditional software engineering stuff over there. Now machine learning and AI and everything came just to make things faster and make things work as easier as possible. That's what deep learning is also doing. Traditionally, there were no deep learning stuff over there. They were just machine learning. There were first statistical models, right? Statistical models were there. Then people sat down, did some research, and realized that we can actually make these statistical models better. So it came to machine learning. Now they've sat down again, did the research, came down to deep learning, right? Even in deep learning, these neural networks and stuff like that, and NLP, yeah, NLP and stuff like that. They were not there. Even reinforcement learning was something that gets recognized not quite long time ago, right? If you remember the rise of Siri, I think Apple was the first company that actually made this one um, quite visible for people to actually know that this is possible. Because whatever, even the research that they did, they broke some time. I mean, they started with natural language processing, and within, I think somewhere in 1919 something in the 90s, they broke over there because they were having some funds around 50 billion, but it was still not working, right? So they just stopped everything because the fund was actually running out. Then later on, they realized that some things can actually help us to do better. Now, even if you take neural networks, for instance, right, they were actually not using efficient tools like TensorFlow. TensorFlow just came, and then now everything just shifted to TensorFlow and the likes of Keras, right? Now you are there by 2 months, 3 months, 6 months to come, we will hear another thing coming up, right? People are in their rooms, people are in some garage and stuff like that, who are always doing this over and over again. They just don't get tired of this. They always do research to make things better. According to them, they are always making things better. All right. So it's just building on top, on top, on top, on top, on top. That's what is actually happening. Right. Just like we have statistical model, it was working. Now we got to machine learning. Machine learning is working. We are not satisfied. We came with deep learning, right? In deep learning, we've come with a lot of stuff under deep learning, a lot of things under deep learning. Now, instead of maybe doing even the deep learning that we are talking about, the likes of neural networks and natural language processing and stuff like that. Now, even if you use AutoML, I'm sure you heard about AutoML. Now, instead of people doing this machine learning stuff by hand, you getting to know the concept, you can use the pre-designed algorithms that they've built already, right? If you use H2O, for instance, you can use the algorithm that you have built already, that you will not even be doing all these things we are learning over here. The good thing is that if you learn it like this, you have upper hand. If you see the algorithm, you know which one will help you. Otherwise, you might end up killing a person, you might end up killing someone, if especially if you're working in the health sector, right? Or you might end up making the whole bank go corrupt. Because although those models have been built, they work perfectly, all right? And if you study, if you have a little hands-on on this one, right, and you feel like you don't actually want to code things, you don't want to do stuff like this, right, you can easily switch and then focus only on AutoML, because AutoML is actually going to be one of the big things to come, right? Instead of you investing a lot of time learning these algorithms one by one, moving from machine learning, going to deep learning and stuff like that, you can focus on AutoML, right? And then study the concepts, just know the concepts and know what you're using, know what your business goal is, and then know how you want to use it for, all right? You can also do that. So we will never satisfy. Even if things are working, we will still have something to do.
Similarly, AutoML, there is a one more package called PyCaret also.
Yeah.
It's really yeah.
And we will hear another one very soon. They will be coming with different ones, right? We are never satisfied as far as AI is concerned. We are never satisfied, all right? We are never satisfied. We will keep on coming with stuff. We will keep on coming with stuff. We will keep on complicate things at the back end, but we will keep on making things as easier as possible at the front end for people who are using it.
One more last question. Can we can we have on a class on pipelining, making a pipelines in production level?
Okay, I don't know if we can have it in this particular class. I think okay, I'll check and see if we can do that. I'll check. I actually have some projects on that. I don't know if I can.
Because in real time,
Bad part is that some of the projects, the real world project that I do, I cannot actually show them because they are kind of sensitive, and is kind of protected according to the companies. If they give you projects like that, you cannot actually expose it, right? So I wish I can actually show you some of the real world projects and how things actually work at the background, right? The good thing is that once you get to know the concept, right, and you get to do one or two real world projects, you don't actually need to, I mean, be worrying about how things work again. You can actually do that based on the experience that you have on one or two projects, right?
Because now that I have a knowledge on algorithms, so how do I productionize my code, and how exactly it works, and what are the things I need to be focused while doing the productionizing my code? So I'm not experienced in that.
Yeah. I understand that well. For let me just share my experience for you. For me, when I was learning earlier on, I learned the concept just like you're learning. Even those days, I mean, there were not enough projects like what we were doing that you can actually go through and then you actually get to know how things work. You have to actually figure things out by yourself. So what I did is that I just joined team, and not with money, right? If even if it's an internship or stuff like that, I don't actually care about the money. I just wanted to know how they really do things on the field, right? So even if I see internship, I don't go for the ones that are paid, because mostly you'll find about 10,000 people applied for that. All right. And if you really want to know how the things work, right? Doesn't matter where it is, right? Even if they are not paying, or even if it's kind of voluntary or something like that, just take it. All right, and then be that kind of mosquito guy in the in the team, right? Get to smell everything that is going on, right? Get to know how they are doing things, or how things are working in that kind of a project. Before you do one, two, or three projects, right, you will get to know the whole architecture. Not that, I mean, you'll be a perfect in it. No, it's never happens. You still need to know more, but you will get the general overview of how things work, right? That's the good thing. You get to know the general overview of how things work. So there was this I don't know if they still do KPMG. They outsource some projects, and people will be contributing and doing that project. I'm not sure. I've not been checking recently if they still offer that kind of a project. It's kind of their client's project, so they actually seek the help of students that need internship, but it's not paid, right? But it's one of the good things that you can actually get to know how things work. And if it is a project that people are doing that they need more hands or something like that, you can actually apply for such projects, right? Such kind of if it is internship or whatever it is, you just want to know how things work, right? You can do one or two of them, right? And you get an overview of it, because what happened is that you can go through a lot of online courses, right? But you still feel like you are still in a black box, right? You don't actually know what happens out there. What you know is that is what you have learned from the online courses. But what is actually happening there is you don't actually know what is happening in the real world. So for them to open up for you to actually see is when you are part of the team and working on it, right? When you're part of the team and then working on it. For instance, some of the things that I work on right now are related to health sector, right? And for you to actually get to make it's not, it doesn't even happen for their projects to actually get outside, right? It doesn't actually happen. You cannot do that, right? I have the password, I have everything that I can open right now, but it's not something, right, that you should actually do or must do as an employee. All right. So what
Excuse me.
actually I would suggest is that it will be good if you actually do real world problem. Like you don't actually need to know it before you start doing it, right? It never happens until you start doing it before you start knowing it, right? For instance, for me, I started learning machine learning without even knowing a single thing about deep learning, without knowing anything about I didn't even know there's something called Flask that you can actually do those kind of stuff. I didn't even know. What I wanted to know is that how things are working, right? So even if I apply for some of the real world projects and they are doing it, I don't even know where they are starting from and where they are going. But once the problem is there, I know there is a solution. That's when you start figuring things out, right? Now you actually know there's an algorithm, there's a problem that you can call classification. There's a problem that you can call clustering. There's algorithm that you can use for those problems. It's actually a plus, right? That you can actually use to your advantage. So what I will suggest is that even if it's an internship or even if it's a group that they are doing a job or they are doing a project that they need hands, right? Just volunteer for one of them, right? Um, out of knowledge, for the sake of knowledge, you just volunteer for one or two of them. You will get to actually know how things before you finish. You will get to know how things work, right? It's better to practice what is actually happening over there.
Can you please share your experience? What kind of challenges usually people face on a production level?
Okay, the one of the challenges is that the ones bringing the problem to you, they don't know what they want, and if they don't know what they want, it's actually difficult to give them a solution, right? And one thing is that this kind of AI and stuff are quite I wouldn't say tricky, but a little bit tricky, right? You can build whatever they want for them. The next time they will come back and tell you that this is not what they were looking for, right? And trust me, it might be a month or two that you have invested in building that, right? So if you are going to do that again, if you are not
Okay.
take care, you forget about it and even leave the company. All right. And the thing is that some of the problem that they will express to you, you think that you even imagine how they think about you, whether you are some kind of a god that you just arrived or something like that, right? They can they can come to you, have a meeting with you, and then describe the problem, right, to you that you if you don't take care, you even laugh, right? Like
Usually, we will translate their business problem into a technical problem. There
yeah,
we
so
feel the client
that's
and then we move forward, right?
that's one thing you have to actually have as a data scientist. You actually get you the more you do it, you get to know that people don't know what they want. That's the advantage that Apple took, and they became that kind of big company that they became, right? If you consider the Apple product that they produce, they don't produce things that we want, right? They just produce the thing and then tell us that this is what we need, so we should go for it, and we will go for it, right? So that's what is one of the things that as a data scientist you should have, right? They will describe the problem to you. After describing the problem to you, you need to actually communicate it back to them that this is what you are saying and this is what you need. Then they will begin to, yeah, you are right. This is what we wanted to say, right? This is what
Yeah.
we wanted to say. Because they will come and then they will tell you that, for instance, they will come and then they will be telling you that we have several patients that come to our hospital, right? Now, if a patient is sick, right? I want the cashier to actually recommend the drug to the person, right? And then go straight to the like most of the hospitals are having their own drugstore that you can easily pick the drug from there without going to the hospital, right? They want to reduce the traffic. So if the person comes to the counter and say that, oh, I want to see the doctor, then the person sitting at the counter will say that, what is your problem, so that I will direct you to the right doctor, right? Now, to the hospital management, they want to reduce the traffic on the doctors, right? They don't want to employ more doctors because paying doctors is a huge expense. So they want to reduce the traffic that goes to the doctors so that they will not be paying that. So if they know that the sickness you are bringing is actually something you can easily get some drug and then cure it, they will not actually recommend you to go to the hospital, to the doctor to waste their time. You can easily get the drug. So what they want to do is that you build an algorithm for them that the person sitting at the counter there, right? If the person say that I have fever, I have lost taste, and I go to the washroom quite often, something like that. Then your algorithm should predict if that cashier or that receptionist put those messages into the algorithm you have built, right? It should predict that this is fever. So the person should direct that person to the chemist rather, not to the doctor. You get the scenario that I'm giving over here. So for them, what they want is that they want something like they will come and describe it like they want some application like maybe I don't even know how to say it, but just some application that as soon as the person arrives and starts speaking, that thing should say that should thing should ring, ping, 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 go to the chemist, something like that, as simple as that. But if you listen to that and you build that kind of algorithm, you end up killing people.
Okay.
For them, what they want to do is to reduce cost. That's their main purpose of doing this, right? And sometimes they compromise the health of people to money. Trust me, every business major target is money, right? So there's part of this kind of data science stuff that you also have to know. That's the emotional part, right? You also need to put your common sense to the table that they want money, right? What they want is to reduce cost to make sure that their business grows. So you are standing in front of the two. Now just imagine you have to reduce the cost. You have to consider the life of people. Remember, if the person says that I have fever, I go to the washroom quite often, I've lost taste, and you say that that thing should be a fever, and they go and give a fever drug to the person, whilst that sickness is not actually a fever. You've killed someone, right? And it came from your model. You get it? So you have to stand between the human parts and the management money parts, right? And figure that thing out. So it's quite tricky if you work in that kind of a field, right? If it is kind of e-commerce, if it's e-commerce, you can compromise and do that. If customers who come to the website to buy stuff, if the person has bought an iPhone first, right? If the person come again, I can show an iPad to the person. That I can compromise and do straight away for you, right? That if that person comes again, I know that this person is a high spending person. So I show that person high spending products, right? I will not go and show, some Nokia phone, which is costing some 3,000 rupees. I will not show those kind of products to the person, right? I will build the algorithm in such a way that if that person comes to the website, I will show this kind of product, some the likes of Samsungs and iPhones, those kind of products. That one is not a problem. But if you're working in such sensitive field like banking, for instance, right? Banking, for instance, if they give you some kind of scenario and then you think about it and you can see that they just want people who collect, say, a loan and then pay back. But if the person is even having a potential to pay and the person has defaulted once, that person should be disqualified automatically, right? That's what they will describe to you totally. But you yourself should actually know how to go about this one before, if you do that, right, you end up cutting the profit of the company too, right? And they will come back to you that your algorithm is making them run at a loss. But forgetting that was their words, that was what they said to you, and that's how you followed and then you built the algorithm, all right? But if you build that algorithm for them and they start losing money, they will come back to you again and tell you that what you did was the worst thing they have ever experienced, right? But if you had give a room, like maybe you give an error rate of maybe say I want, instead of maybe going for say 98%, I can go for say 94%. all right? And then I'll follow up and then see how the thing is going up and down. Then I'll see if I need to improve or I need to even give more room, right? So that should be something that you should know, that you should actually be knowing from back to back. And it comes from time to time. It won't actually come at once, right? Sometimes especially when you get your first job, right? And then the business guys will sit you down and be describing their unimaginable philosophies to you and what they want to achieve in the next 5 years. They want to be the biggest company in the world and blah 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 blah, and they will end up asking you to do those kind of the thing as if you are the superhero. You just kind of perform magic and things happen, right? They will just give you those kind of things. And you, if especially if that is your first job, the only thing you will focus on is to make sure that whatever they said, you're doing it.
Okay.
Right? If it is your first job, that's what you will do. That's mostly about, I mean, about 98% people will be doing that. But if you do it for maybe 3, 4, 5 years, you realize that not everything they say is what they mean, right? They don't actually know what they are talking about.
Okay.
So that becomes your job to figure it out. That's why they say the data scientist guys become the superheroes. They need to know everything. They need to know the domain. They need to know the algorithms. They need to know blah, 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 blah. Because those who are coming to speak to you, you need to even know more than they are speaking, right? Otherwise, they will end up guiding you to do something that they will come back to blame you.
That's fine. Then in industry, how important as a data scientist to know this Dockers and the Kubernetes? Is it necessary?
Very, very, very necessary. Very, very, very necessary. Some of the companies, even if you don't have those skills, they will not actually employ you because, I mean, if you like, if for instance now we are doing everything in Jupyter Notebook, this one means nothing. What would you do with the Jupyter Notebooks? Right. This one is for learning. This one is for you to get to understand the concepts, right? Now, after getting to understand, if you don't start from here too, you will not get there, right? So after getting to understand the concept, now you need to move one more steps, right? If you go to the company, for instance, you will not be doing anything in Jupyter Notebook, right? You will not be doing things in Jupyter Notebook. Everything that you do should be, should be in production. It should be working, right? It should be working, but not something you do in Jupyter Notebook and submit. For them, they are not even interested in whatever you're doing. What they are interested in is that they will search maybe if for instance if Zomato has employed you, whatever they want is that they see the app, they can track the delivery boy and it's working. That's all they want. Whatever you did at the background is not their problem. They will not even ask what you did. Those guys who will be asking are the auditors, those auditors. And this time they even hire auditors from different companies. So maybe if Zomato is hiring a data scientist and that data scientist is performing an algorithm, they will open that algorithm to someone who is, who is in, say, Amazon, right? Normally, if Zomato is hiring data scientists and that data scientist build an algorithm, they will never make it known to someone who is in, say, in Swiggy, because Swiggy is their competition, right? So they try as much as possible to protect that algorithm so that Swiggy will not steal it and also use it, right? So what they will do is that they will get someone, a data scientist who is in, say, Microsoft, right? That person will come and then audit your code and see that things are working. And that guy, if that guy, since they've paid that guy to come and audit you, when he comes with all faults in him, all the unnecessary things he wants to vomit out. He just come with all those questions and be asking you all the unnecessary things that he's not even supposed to ask you, be asking you because they've paid him. So he actually want to make an impression so that they will continue paying him.
Okay.
Yep.
Thanks for the very good insight.
Okay. If there's any other question we can talk about, else we can drop here. And one more thing, if you are going into data science domain, then it's better you associate yourself with the people who are already doing it, right? On LinkedIn, for instance, there are people who volunteer to be there, to be a mentor or something like that, right? You can send about 20 or 30 people messages, right? About two or three will reply. Some of them will not even look at your message, but some will reply, right? Some who are working in some big companies or stuff like that. Some will reply, and then they can be also giving you some insights, right? It's easier for someone to hold your hand to show you where you're going than you going there by yourself, right? Getting doing a lot of errors, going here and there and coming before you know the right road, the time is already gone, right? So if you get about two or three of the people who are already working as data scientists, right, then not taking one person's opinion. Sometimes opinions or two are biased, right? Someone can give you an opinion based on his experience, right? It's just like the model you are building, based on the data you are giving, that's the result it's giving you. So based on the person, what the person thinks about data science, what the person has experienced, those are the advice the person is going to give you. So if you have about two or three of the people, you can seek advice from either of them, and then at the end of the day, you can actually filter those advice out, and then you can take the one that suits you the best. For me, when I was speaking, I was having about five different mentors that I actually go to when I need to ask something. And this an actually easier way than searching on Google for answers. Okay, so if there is no other question, then we can end here.
Thank you.
Okay, thank you. Good night.